Well, welcome everybody to our cloud computing tutorial. I'm Naomi. I'm gonna be asking you questions that I want answers to. So like if you join my Slack channel, Alterman Cloud, then we can all have a rousing conversation there. In addition to in person. And hello people online. Hello Tien, hello Daniel. Let me see. We got two folks coming in from online. Welcome.
Hi there.
Hello. Tien and Daniel, where are you calling in from?
Uh, Philadelphia.
Nice. That is very close to where I grew up. I was an hour outside of Philly. That's southern New Jersey.
Oh, nice.
Yeah. Tien, where are you calling in from?
I'm also from Philly.
Nice. Yes. Cool. Got Philly people. So wait, does that mean, oh, it's like 6:40 with you guys?
Mhm.
Correct.
Well, I hope you enjoy this evening cloud tutorial. And for all of you, I hope you enjoy this mid-afternoon cloud tutorial. Thank you for spending some of your Friday afternoon with me. It's touching to me because there are a lot of things I know people like doing on Friday afternoons. So since we're going to be hanging out for the next hour and a half, it's a little bit about me. I'm a technical education specialist here at the University of Washington. In practice, that means that I help people figure out how to take technologies they're interested in using and adopt them into their workflows, get to know them more, get to know whether something is relevant to the work they do. I like describing myself as like Miss Frizzle from the Magic School Bus. If any of you guys seen the Magic School Bus before, that's kind of the energy I try to embody when I'm on my best days. When I'm on my worst days, I'm sort of just a puddle. But you know, we've all got our mean between the extrema. By training, I'm an electrical engineer, and I've done a lot of research into computer networking back when I was doing my master's degree. So that's sort of what led me to be aware of and then embedded in all this cloud computing stuff that we're going to be talking about today. And I think over the years in my career, the way that I've grown to define what I'm interested in and what I like doing is understanding the flow of information between very complex domains of knowledge. So one way that you could think about that is I'm interested in how computers talk to each other. I'm interested in how we talk to computers by writing code and how that code gets run by a computer. I'm also interested in how we talk to each other because we are all individually very complex systems and we figure out how to have some sort of exchange of information over a conduit. So today we're going to be talking about cloudy things, specifically what cloud computing is and the fundamental abstractions that we use to talk about it. We're going to tour some common workflows for cloud resources, that is to say, how people take all these different things that the cloud can mean and harness them to do stuff that they want that's meaningful in their lives. And then we're going to discuss meta skills for how to use the cloud effectively. This is actually, I think, the most important thing when figuring out how to use cloud computing, because a lot of it gets thrown at you as things that people are trying to sell you. Amazon is going to try to sell you their SageMaker notebook platform for AI alignment, blah, 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 blah. Microsoft is going to try to sell you their cold storage, object storage, blob, database management, Cosmo DB, whatever. None of that actually necessarily is useful to you, but understanding how to hear what they're saying and integrate it into your understanding of the actual concrete work you do, that's what we're going to be really trying to figure out today. Before we go any further, though, I like doing this sort of level setting for myself to understand where you guys are at. I'm interested in what you've done with cloud computing before. And so there is no wrong answer to this prompt. I don't want you to send me a message just yet. I want you to type it into Slack and then wait to hit enter till I tell you to, so that I get a flood of messages. What is the most advanced thing you've done in the cloud? For any definition of cloud. I'm looking for serious answers. So like you could say, I have frolicked under the clouds. I have just frolicked under these clouds. But I'm looking for like an earnest answer of like, this is a thing I've done that I think of as cloud computing. Use jargon. Use fancy words that would make people go like, I don't know what that means. If you don't know any jargon, that's great. Use the most fancy words you can think of that you understand to describe what you've done with cloud computing. The reason I'm doing this is because I want to understand what you guys have done before so that I can talk to you more effectively now. So type out in Slack and wait for me to say hit enter. What is the most advanced thing you've done in the cloud? Does not matter if it's not advanced. In fact, if it's not advanced at all, the secret thing is if y'all are like, I've never used anything in the cloud before, that's great because this slide deck is aimed at people who have not used the cloud at all before. But I can help level set depending on what people have done. Like, I'll know, okay, there are some people who know what this means. There's some people who know what that means. So I can speak to different levels of complexity. All right. Why don't y'all hit enter now? Okay. Running MRI data on a supercomputer. Fit models on HPC. I'm seeing a lot of HPC so far. That's great. Remote desktop and sharing files on OneDrive. I've used AWS S3 to download and upload data. We are going to have a slide that describes exactly what that is. Prepared a pre-processing pipeline for various EEG datasets from my lab. Pre-processing pipeline. Nice. I run analysis on a remote server. I ran my fMRI pre-processing code in the college server. This is making me super happy. So y'all have already thought a little bit about how you take code that you might run in one computer or one machine that's close to you and do that work somewhere else. What are the tools that you use to remotely access machines and data? Downloaded data from my center's cloud. Okay, well, this makes me really happy because I think that this is going to happen to be just about at the exact level that like we can really get some good discussion going on. So when I say cloud, that can mean a number of different things. This is all relevant because when people use the word cloud, they can really be talking past each other and not exactly understanding the consequences of what they mean. How many of you have heard about the UK Biobank and their changes in data access in the past few years? Like come up. So the UK Biobank is a source of a bunch of human-centered test data, test results. It's I think there is neuro stuff in it and genetic stuff, but there's also a lot of qualitative data and just a lot of like longitudinal study data. It's a whole lot of stuff about people, so that if you want to conduct a study that looks at people aged 18 through 25 and their predisposition towards having neurology issues, you could find that information in this database, or you could synthesize it out of the raw data. A few years ago, they made a change where the only way to access this data was by doing any computation you want on the data in the cloud through their cloud computing platform. There are a number of reasons why they did this, but a lot of people were really disturbed because they were used to downloading the data to their center's high-performance computing cluster, or downloading the data to their laptop and using it from there. Ultimately, I would pose that it's not really a good or a bad thing that the UK Biobank said you have to use our cloud computing platform to access our data, but it does mean that people who didn't have those skills had to take a break from the research they were doing and develop an understanding of how to do what they want in this place that is not their laptop. And so it's really useful to understand what people may ask you to make remote into the cloud or into a supercomputing center, and how you do that cost effectively, how you do that computationally effectively. What we see is really this swinging pendulum of having high-performance computers that we do data crunching on. And the way that you interact with these things is with, we call this a dumb terminal. So there's actually no computer in here. It's just a monitor and a keyboard. And this would be in the like 70s and the 80s. This would be hooked up to this, and you would get this to run your experiments for you. This is very similar to a modern day HPC cluster. It just looks way groovier. And what we found was as computers became cheaper and easier to put a lot of power into a literal laptop, we moved them into the office. We figured out how to have your workstation where the computation gets done sit right under your desk. And so suddenly it's a challenge to figure out how to take large amounts of data and distribute them to the computers in everybody's offices. But it's useful because everyone can now do their computation under their desk and they don't have to wait for each other and get kicked off when, like, I'm sure if you've used HPC clusters before, you've had to wait for the scheduler to take your job, and it like once it finally runs, then it like stops halfway through because of some coding error, and then you have to wait again for the next round. You can imagine why it's really nice to not have to deal with that. But the problem is, this thing can only do so much. They're always going to be able to stuff more of this juice into this box than they will this box. And so we see the pendulum swing back to HPC clusters. This, I think this is a generic data center picture. I have pictures of the HPC system that the University of Washington uses. It's called HIAC. Hello, HIAC people, if you're watching. You access this HPC cluster from your laptop. It's a little smarter than that dumb terminal from the 70s we saw, but ultimately, it's doing the same thing. It's being a screen and a keyboard for code that you wrote that you're running on these things. The pendulum is now swinging in a new direction in which we realize universities don't really want to be spending the money to buy all these machines and maintain them and pay for the power and the cooling and the personnel to keep track of them. Furthermore, sometimes they spend that money, but there are too many people using the HPC cluster all at once. And maybe you got a bunch of money from some funding source that allows you to do your work and pay for computers to do the work on, but these things are all filled up with people doing research. There's no space on them. So what we found is that these private corporations had a bunch of computers in a data center just like this one that they weren't using all the way. They had some that they were just kind of letting sit there idle. And so they realized they can rent them out. That's actually where the modern idea of cloud computing came from, was Amazon bought a bunch of computers and built a really nice system to flexibly assign workloads to different places for when you were buying books or toilet paper on Amazon.com. And they realized only like a third of our data center is in use in the middle of the night when people aren't shopping for things. Or the only people shopping for things are probably not completely sober and making bad decisions, which is a much smaller amount of people than the whole populace. So they said, well, let's rent for an hourly rate the servers that we have in our data center to whoever wants them. And that turned out to be a really good business model. That turned out to be so good of a business model that Amazon started doing a lot of that and buying data center hardware specifically for the purpose of renting it out to randos like us, rather than using it for their internal website. And then Microsoft said, whoa, I want in on that. And then Google also said, whoa, I want in on that. And thus we have the ability to rent time on computers owned by these three for the purposes of running our code. When I say cloud, that's what I mean. There are a lot of different things that cloud can mean, but in the context of this tutorial, and really in the context more broadly of research computing, we're talking about this when we talk about cloud, rather than Google Drive or Google Colab even. So I want to, I have two prompts here. I have, what are the pros and cons of paying someone to manage your computers for you? And then I have another question, which is how might renting compute, instead of buying it, change the way you ask scientific questions? Which of these questions sparks more joy to you guys? Which one do you want to answer? This one? Very good. All right, type out a response to this question. Wait until I say go to hit enter. All right, if you have your answer, then why don't you hit enter in 3, 2, 1, go. Ooh. forces us to place a higher value on efficiency when planning analyses, because if there isn't infinite access to compute, well, it costs something. Data privacy is an issue concern. Also, cloud computing is much more expensive than HPC. I have to be economical with how much time I have to download data. How much runtime do we have? The question is really, how much money do you have? You have as much runtime as you have money to pay for it. Questions that can be applied to different types of data. This just fundamentally changes the types of things you may be doing. I like it. Ooh, you got to modularize your analysis pipeline to run in parallel and small chunks. I really like that. That's cool. Yeah, there's this fundamentally different way you might use these computers that are in this data center that your HPC cluster might not have allowed. So now your experiments are built on really different types of computer code. I like asking this question because even though public cloud platforms like Azure and AWS are very similar to HPC clusters, I think that it really subtly changes the way we do our work when we subtly change the medium in which we do it. You know, the way in which I give this presentation is super different because I have a laptop and a slide deck than it would be if I had literal physical slides, even though they're physically result in you seeing something on the screen. Like, these things are worth thinking about when you begin adopting new technologies. So anyway, after being philosophical for a second, let's get concrete. I like talking about building blocks because without that, we can really easily just be talking about completely different things. When I say building blocks, I mean in the sense of if you logged into Google Drive, which is a consumer cloud platform, that is to say, a cloud platform not for doing computing so much as people might use for free or pay a little bit of money in order to have Google Docs that are not on their computer, so they're backed up elsewhere. The building blocks for a Google Drive account are word processor documents, spreadsheets, slide decks. I have a Google Drive account and this is a slide deck in it. That's sort of the fundamental unit of thing that I might have in Google Drive is a document. Now, we can talk about cloud computing in the context of something managed for you. Here at NeuroHackademy, you have access to a Jupyter Hub, which has some data on it. You can run computer code on it, and you can do that by creating a Python notebook. Or maybe you have a Python file, and you open a terminal and you run the code in your Jupyter lab through that interface. Maybe you use the Python console. I'd argue that these are the building blocks of your experience when you're on Jupyter Hub. So the question that I'm about to answer is what the equivalent is if we're talking about this kind of cloud, which some people, computer IT people, call this the public cloud. I like calling it infrastructural cloud because unlike consumer cloud, which is an end consumer product that you can just pick up and start using immediately, and unlike a managed cloud platform where you didn't have to set any of this up, Noah and Ariel set this up for you. This is just providing you the ability to build computing infrastructure. These platforms are how you build an HPC cluster or how you build a Jupyter Hub. There's a guide to how you set up a Jupyter Hub at the bottom of this slide deck. And those things aren't usually worth our time to do as individual researchers, but they're good skills to know that you can pick up if you ever, say, run your own lab or want to run an event like this one, knowing that you can set up a Jupyter Hub for the people who show up to a workshop. I was doing an intro to programming workshop at UW Bothell recently, and I wanted to be able to get my students up and just playing with code very quickly. So I spun up a Jupyter Hub like the one you're using on Azure, using a few systems and tricks that I've picked up by doing this stuff a lot. I set up this computing platform for people that the students could log into in like an hour, 2 hours. And that ended up costing, I think, about $10 total for the 1 hour that I had 20 people in a room playing with computer code. It's not nothing, but I wouldn't have been able to do that, period, if I hadn't been able to just rent time in a data center. So our abstractions, our building blocks that let us build those Jupyter Hubs and build those Google Drives are, of course, computers, things that run code. They have different brand names on all of these different services. by and large, they're called virtual machines because you can think of the cloud as containing a bunch of hypothetical physical machines that you rent time on. So virtual machines on Amazon's cloud are called EC2 machines. It stands for Elastic Cloud Compute, Elastic Compute something. I don't remember what EC2 stands for. Azure just calls them virtual machines. Google, I think, calls them Google Compute. Storage is another abstraction that we care about. Of course, there is storage built into a computer. Otherwise, it can't have an operating system. It can't have your profile picture and personal files on it. But sometimes you start working with a lot of data. Maybe you've got 100 gigabytes of data. Maybe you've got a lab machine that's constantly streaming in data and you have like a terabyte of data that constantly changes. If you have a lot of computers that are doing all this processing, then presumably you want to store this data in one place and not have to copy it to each of these machines. So when we talk about storage in the cloud, we're really talking about storage for data sets, storage for things that get shared between machines, storage that you want to keep around even if you throw out one of the virtual machines that you've purchased. So there are a few different ways to do this in the cloud. There is file storage, which is what we would think of as like a USB drive that you plug into a computer to move files around. There's also something called object storage. I saw some of you have worked with S3 before. We'll talk about S3 in just a few minutes for those of you that haven't played with it. This has a billion different brand names, and they all try to be really cute. Azure calls them blob containers. AWS has S3, EBS, EFS file stores. Some version of this slide at some point in the past had Google brand names for these things on it too, but I think I deleted them because Google, actually to my liking, doesn't have cute brand names for things. They just call it what it is. So on Google Cloud, it's probably just called Google Storage, Google Files, Google Objects. So there are a bunch of other fundamental building blocks that show up in the cloud, but really are less important when you're first playing with it. There is networking. How are these things all connected together? If these were in a physical lab, you would have to get literal Ethernet cables and plug them into all these different things. There is users and security. Who is allowed to purchase and get rid of virtual machines? Who is responsible for paying the storage costs here? Who is allowed to access certain files in this storage? The term that shows up across the cloud platforms for this is IAM, Identity Access Management. If you're ever doing cloud stuff and you see IAM show up, what that's really saying is who in your lab has access to screw with this stuff. You can think of IAM as really like taking your like ID card from your university and using it to swipe into a lab room, which is different from being able to log into a computer. There are still normal computer accounts in here, like a Windows account or a Mac username and password. Separately, IAM is saying who has access to the debit card that you use to buy these machines. Who has access to the physical space they sit in. It's all virtual in this case, but the concepts are the same. As is location. You don't know where exactly in a given data center these computers are, but you do get a choice over which data center they're placed in. And I mean that physically in the world. There will be different regions that you select when you use these cloud platforms that say, I want to rent a virtual machine in Microsoft's data center in Iowa, or in Amazon's third data center in Bristol, UK. The reason why you might choose one location or another might be because a collaborator of yours has data that's already stored in one of those regions, and so it's going to be much cheaper and faster to access if you put your computers next to where they have their hard drives. Maybe you do this because all of the GPUs that you want for your machine learning are being used in North America because it's daytime here right now. But if you rent a GPU machine in Indonesia right now, then it's the middle of the night. These are reasons why you might hop from one region to another, and why you're always sort of thinking in the back of your head where things are located in the world on the cloud. It's not important that you rent machines that are physically right next to you, but it is important to think about where things are and whether you are renting things that are near other things they need. Does your code need access to data? Put it close to the data. Are you uploading data? Put it where all your different machines are. I also have this little corner thing, blank as a service. This is a small corner of this slide, but it's the biggest thing that all these cloud platforms try to sell us. What they say is, hey, you, I bet you're a neuroscientist. You don't want to bother installing and setting up all this software, figuring out how to configure it. You just want to run code in a Jupyter notebook. Well, we can provide notebooks to you as a service. We can provide backed up file storage to you or a database, a SQL database as a service. So there are all these different value add, like we set it up for you. You don't have to worry about as many details, things that they will do. And these are broadly classified as platform as a service. The deal with those is that fundamentally, usually they don't cost anything extra. They are all, at the end of the day, running on virtual machines. It's just that the cloud platform is doing some extra work for you. And the thing that they get out of it is that it makes it much harder to move to another cloud platform if you have to. The thing you get out of it is that you have less to worry about, which is a pretty good deal. And by the way, I am, talking a lot, but like, if you guys have questions or thoughts while I do this, this is a small enough group that, just ask me questions. You can also type in Slack if you're shy. I'm actually shy, believe it or not, when I'm not in like teacher mode. Yeah, before we go on, someone asked me a question about this. There's enough here that I know someone has a question. One of you.
I have a question that's not necessarily related to this at the moment.
Yeah.
I thought that Oracle also had cloud services, like they had cloud infrastructure.
That's a great question. Yeah, so. And sorry, what was your name? Isla says, doesn't Oracle have some sort of cloud thing? Oracle absolutely does. Oracle's cloud is called Oracle Cloud Infrastructure, OCI. IBM also has a cloud. It's called IBM Cloud.
Those just not for research purposes?
Are those not for research purposes? That's a good guess. They are just smaller. People just use them less, but they are just as applicable to research as the others that we've been talking about so far. Amazon was the first public cloud. Azure and Google, or Microsoft and Google followed suit pretty quickly. And so those three those are the big ones that have all of the customers and all of the press and notoriety and big business deals. Oracle and IBM are both great platforms. And pretty much everything that we are talking about today applies just as much to Oracle and IBM's clouds as it does Google and Microsoft and Azure's. Thank you for asking about that. The only reason I don't put them on the slides is just because when you add a platform in these workshops, it actually squares the amount of information that you need because it's that platform for every topic. So I would need to look up many more brand names and links, and I was slightly lazy. But IBM Cloud is, we'll talk about this at the very end of the day, what the different clouds are good for. The spoiler is that they're all pretty good at pretty much all the things all the other ones are good at. Oracle is really good at databases and data storage because that's Oracle's bread and butter. That's what they're trying to get people to buy. IBM has a lot of different things that it's good for. They have a really interesting quantum computing platform. I didn't know that quantum computers were real until like 5 years ago. And then it turns out, no, they're real. They're not useful, but they're real. They're not useful to anyone other than quantum computing researchers. They don't actually do anything magic, but they do interesting things. In addition to IBM and Oracle, there are a few other cloud providers. You'll often see much smaller ones pop up that offer something like, we built our data center right in the middle of a wind farm in the Texas Panhandle, and that allows us to get really cheap energy and cooling. So our virtual machines are half the price as these other places. And that's great. The problem with those platforms is just that if they get bought by someone, then they disappear. Or if they go out of business, they disappear. Not a problem for researchers, because we hop onto wherever we can get funding to work. But it does mean that it's hard to keep track of where they all are. So there are a lot of different cloud platforms. The key is all of the other cloud platforms, by and large, do whatever it is that Google, Microsoft, and Amazon do. They're the ones who set the stage, who like define the terminology that we're using. Because they were there first and they have so many customers that they really figure out what the patterns are that we need. And they're all good for research. In fact, the smaller ones can be better for research than the bigger ones because the bigger ones don't need us. They're like, the NSF wants to come and bring hundreds of millions of dollars to our cloud platform. That's cute. I get that kind of money from 3M in a weekend because someone forgot to turn off one of their mega compute clusters. In truth, the amount of funding from research going into these cloud platforms is so minuscule, and this is actually a really good meta skill, is so small that they do not speak researcher. We have to speak the language they do in order to understand their documentation, in order to understand their user interfaces. The language they're speaking is IT person who works for a gigantic multinational corporation that sells body wash in 17 different countries. They're the people who spend enough money on these things that they start actually catering to them. And we just sneak in like little mice and use their compute at night. Very good question. Any other questions before we talk more about virtual machines?
I
Yeah.
have a big one.
Yeah.
It's the page data access stuff. Is that also running this stuff?
This is such a good question, and I actually don't know much about that program. Let's look it up. NIMH Data Archive?
Yeah.
Is that it? Ooh, human subject data available across many.
I was trying to get, well, my lab's trying to get access, which is why I was asking, but
Yeah.
some weird data rules that were like, you have to run it through our platform. I think it's S3, but I'm not totally sure.
This sounds a lot like the UK Biobank. Yep.
Yeah, I have the same issue because right now there's like a new NIST is what they call requirement for all NDA data. That is like all none of the high performing cluster is gonna be conforming to the NIST. So we also have to move to AWS because of this.
That's unfortunate. Yeah. I would have to read more about this when half of my brain wasn't like split into social reading the room teacher mode. But my guess is that so the deal with the UK Biobank is that it's built on top of this stuff that we're talking about, but it doesn't actually give us access to that layer of infrastructure and understanding. Like they built their data access platform on Amazon's S3 stuff, but like we as researchers have to log in through their portal and do things through their interface.
Yeah.
And so this is the kind of thing where the stuff we're talking about in this workshop can be useful if you want to do similar things with your own research that you can allow other people to log in and access your data, or give you an underlying understanding of the stuff that they're building these platforms on top of so that you can ask good questions when it comes to negotiating with them or dealing with funding or things like that. I will take a look at this. I actually don't know what platforms this runs on, but it's a really valuable question for me because I like knowing what you guys actually are dealing with. This is helpful to me to make this workshop worthwhile. Anyway, I'll take a look.
I'm fine for access to Or you can see this stuff, like I can see that stuff. I don't know how far you can go. But you can look at that, you just can't look at anything.
My suspicion is if I tried to look at the actual data or work with the, then it would, yeah. Well, because it looks like this is like built like a store, like filter cart login. It's possible. I'm not sure how this platform works. I have seen, they're called, by and large, these things are called science gateways, which is to say there is data or compute resources that they want to make available to scientists in the field. And it costs money to do that, so they need some way of tracking what labs, what people have access to these things. So some science gateways are set up such that when you buy this access, what they do is they give you some low-level cloud things. So they'll say, here is, and I'm going to use terms that like don't have to make sense to you guys right now. Here is an S3 bucket URI and an access key that we're going to rotate 3 times a month, and like it's in this region in Amazon. So like you are now responsible for whatever you want to do with it, but that's the access for it. So in that case, you're going to use Amazon EC2 to create virtual machines near that data. By near, I mean in the same region in the world. And then do your remote computing there. In the case of UK Biobank, what they were doing was much more like the Jupyter Hub you guys have access to for NeuroHackademy, but with like a institutional login. And so it's varied. There are a lot of different ways that people can do this sort of access stuff. I'm going to read more about this later. All right, let's talk about virtual machines a little bit in more detail. So when we're talking about a VM, virtual machine, they are virtual versions of the computers that we have on our desks right now, or that we log into with HPC clusters. So they have CPUs that run computer code. They have memory that keeps track of variables and data as it's being worked on. They have GPUs, which can do machine learning tasks and also render pretty graphics if you wanted to play the latest video game. It's actually not a cost-effective way to play the latest video game. Way to play latest video game is to have a cousin who works as an IT person who can give you a laptop that fell off a truck. That's not true, just making that up as a joke. Storage. Where are your files stored? How are you saving your code and running it on this CPU? And that storage contains all sorts of things that a computer normally has. It has the operating system. It has libraries like NumPy that you had to install. It has Python. It has a home directory, which has your user stuff in it. And so the deal with these virtual machines is that while they are like real computers, they are, in truth, completely hypothetical constructs that are not physically analogous to a real computer. There is not a real dedicated computer that you are getting when you rent a VM. It's just beaming all of your work and all of your home directory and all that stuff onto a sufficiently powerful piece of the server somewhere. And so you end up getting charged money for how long this thing is turned on by the hour. So if you start a VM and start doing things on it, and then turn it off in like 20 minutes, you will be charged for 1 hour's worth of on time. If you turn it on, do some stuff, leave it there for 6 hours idle, not doing anything, and then come back and do more stuff, you are going to be charged for 6 hours worth of compute. It's not based on how hard these things are working. It's just based purely on the fact that they're turned on. And as soon as you turn them off, rounded to the nearest hour, they will stop charging you for the compute power. One of the really nice things about virtual machines is that because these are not physically real objects, it's very easy to change them in this imaginary world. So you can turn a machine off and make it more powerful. If you're doing like, I don't know, number crunching and you say, man, my data set won't fit in memory, you can turn the machine off and change its instance type to be one that has much more memory. And then turn it back on and resume doing your computation without having to change your software or reconfigure the operating system or anything like that. Yeah, question.
So, how does this virtual machine differ from HPC?
How does this virtual machine differ from an HPC? Really interesting question. they are very similar to HPC clusters.
Mhm.
I think that the biggest difference that you would see as a researcher is that it appears to you as a completely not shared environment. So whatever software is on it is the software you installed. You cannot see anyone else's files. You cannot see the things pre-installed by the people who run the HPC cluster. You cannot see the other people who are running jobs at the same time. It's putting a lot of effort into giving you the illusion that you are the only one who is on the physical computer in the physical data center. There are a few reasons why that is worth it to some people compared to an HPC cluster. But the difference is really just sort of that they came from different origins.
Okay, so
Yeah.
I only did PH because I know where they were talking about this.
Yeah.
When you submit a job, I submit a job to different
No.
workers nodes.
Yeah.
But here you get that like you already at the beginning have all the virtual machines. So do you work on that or do you do submit jobs?
Yeah, you do not submit jobs. So you, I don't know how your HPC cluster works, but like, do you like log into like a boundary box, a gate? Like, you log into something that you can submit Slurm jobs from, you know?
I do that on
Yeah, on a terminal.
Oh, yeah, of course, yeah.
Yeah, so the way that this looks is that instead of logging into a terminal that you can type Slurm things into,
Mhm.
or have you ever submitted an interactive job in Slurm? So like if you submit an interactive job in Slurm, then instead of just doing the thing that you specify in the job file, it gives you a terminal that you can run commands and code from one of these computers that has a lot of RAM and a lot of CPU and a lot of all this fancy stuff. So the idea here is that it's really like skipping the Slurm part and going right to the interactive terminal that lets you run commands on a powerful computer. Or a really unpowerful computer. That can be a way that this is the opposite of an HPC cluster, is that you could rent a super cheap computer that has almost no resources, which is really useful for certain tasks. Like say, if you wanted to conduct a survey that involved emailing people once every 6 hours. For some stupid reason, I don't know, like, I can make something up, but like your research involves sending emails to people every 6 hours for some.
Actually, I never, I don't study like that.
There you go. So like, there are like, when I said stupid reason, I was like, what I would come up with would be
Yeah.
stupid. There are legitimate research reasons to do that. So you could rent a computer that costs 6 cents an hour to run all the time, 24/7, so that every 6 hours it sends these emails out. Because you don't need a lot of memory, you don't need a lot of CPU. And that's something you wouldn't be able to do, certainly not on an HPC cluster, but even if you were buying a physical computer, because they don't make computers that small. They do, but like, a bad example, they do. They're called Raspberry Pis, they cost like $30 and they're really good. I love Raspberry Pis. There are other reasons why you would not want to do that for your email research job. So a big difference between this and an HPC cluster is that generally with an HPC cluster, you're talking about the reason the university can get away with buying that much compute power is because they're doing it in bulk. And at least at the University of Washington, in order to get access to the HPC cluster, labs have to buy it's like a condo model where they buy a large slice of compute. And this can cost in the thousands to tens of thousands of dollars a year. And then within that slice, you can do whatever you want. And virtual machines are it's much easier to spend much less money on a smaller virtual machine. And you can do that as an individual. So with an HPC cluster, it might be practically difficult for you to, as a grad student, get time on an HPC cluster if your advisor or your department does not already rent space in that cluster. But in this cloud stuff, if you were to apply in a grant and say, we need this much money for cloud compute, admittedly, it's much more expensive than an HPC would be minute per minute. But it's also much easier to get. So you can apply for a grant from, I don't know, the CDC or the NIH or whoever, and say, I'm going to use this much money for cloud compute infrastructure. And then within that grant, you can use that to bill for virtual machines that otherwise, like, you might spend a couple $100s on cloud compute that would have just been too small to ever do on an HPC cluster, but too big to do on your home laptop. So I'd say it's the long answer, but I think the fundamental difference between these things and HPC. Yeah, thank you. It's a really good thing to discuss here. Something I want to emphasize with this is this rather grim phrase, cattle, not pets. The idea with a lab purchase, if you use your grant to purchase a laptop, is you care for the laptop. Maybe like you would a pet, you give it a name, you put stickers on it, you care deeply about this machine. I've had this laptop since 2022, and it's become a very close friend of mine. Just kind of sad. The idea with virtual machines is that you are going to be creating and deleting them very fast because it's free to create and delete a machine as long as you're paying for it by the hour. But, you know, you don't have to pay for it to get shipped to you. You don't have to pay to dispose of it. You don't have to pay to set it up. So we treat these as a herd of cattle. We treat these as livestock, as machines that we don't grow attached to and we don't give names to, because at any given moment we might delete one and create a new one, or turn one off and change its size, change its fundamental characteristics. We treat virtual machines as a platform to run our code on, the same way that we treat rice as a platform for delicious stuff for fried rice. We don't care that much about the rice. In this context, we don't care that much about the computer as long as we can pay for it and there's enough of this to run the code that we care about. And another nice aspect of that is that if you screw something up and misconfigure the computer, it doesn't matter if you break it. You can just turn it off, delete it, and create a new one. And that actually goes for almost all of these things. If you break it, if you screw something up, that's okay, just delete it and do it again. It doesn't end up costing you that much, with the exception of data. If you screw up your data, then obviously you can't get your data back. So it's nice to have backups. But other than that, there is a very low cost to experimenting on the cloud. If you're not sure that you need something or you're not sure what something does, as long as you understand the rough pricing structure for it, am I being billed by hour? Am I going to incur lots of costs if I leave this on overnight? Things like that. You can explore with these things and play with them. So the reason why we talk about instance types as opposed to just these being knobs that you can change like incrementally a little bit more RAM, a little more memory, is that there are all these pre-made configurations of virtual machine that the platforms will give you access to, and those configurations have names. So you might be renting a virtual machine that is of type P4D 24X large. And that type of machine costs $32 an hour. It has 96 CPU cores, so that's roughly, I don't know whether vCPU means, it might mean that you can have 96 threads of code running at once, or it might be twice that, like 200 something threads of code running at once. It has a whole terabyte of memory, and it has 8 terabytes of storage, and it has this much network performance. That's pretty expensive. Instead, you could pay 37 cents an hour, and you have 4 CPU threads, and 32 gigs of RAM, and 150 gigabytes of storage. That's much closer to what we might have on a laptop. So this is the kind of thing that you might rent to do the emails. This is the kind of thing that you might rent if you wanted to do a bunch of machine learning on a data set that was really big. That was hundreds of gigabytes big. This is a terabyte of RAM. You cannot buy things with a terabyte of RAM that you just sit on your desk. If you want to buy those things, then they usually come in the form factor of, like, you know, these data center machines. They look like pizza boxes. So the problem with this stuff is that we grow to have to understand what all these different names mean in order to find the type of machine that we're interested in. And that can be a huge pain in the butt. So this is how I would break down it being, this is how I would think about figuring out what type of machine I wanted in the cloud when I'm looking at all these different virtual machine types. When I showed you this list, these all start with a letter. This is the virtual machine series. And broadly speaking, this is saying that machines with a G in front of them are generically useful. They have memory, they have CPUs. Machines with an R in front of them might have some different property. Maybe they, by and large, have a lot of RAM, or maybe they have a lot of storage. So if you want computers that have a lot of CPU cores, they can run a lot of code very fast in parallel, but you don't have big data sets, go for a compute optimized virtual machine, something that has a lot of computer in it and not a lot of memory. If you have a huge data set that you want to be able to pin through and look at individual things about it, but you're not crunching a lot of numbers, go for a memory optimized virtual machine. GPUs are really expensive, so if you're not doing machine learning, don't pay for a GPU because you're not going to need it. But if you do need it, then go for a machine that has one. So these are the different series on all the different clouds for all these different things. So if you're on AWS, if you're on Amazon, and you just want a generic virtual machine, go for a machine that has T at the beginning of the name, or M at the beginning of the name. If you are on Amazon and you want to fit a huge data set in memory, look for a machine that has R at the beginning of the name. Yeah, question.
Why are GPUs better for machine learning?
That's a great question. Why are GPUs better for machine learning? So a lot of the fundamental work that machine learning is can be reduced to linear algebra, which is to say matrix multiplications. And that is the mathematical work that GPUs are built to do quickly and efficiently. Whereas normal CPUs are built to do individual calculations one at a time. So for machine learning, they'll have things like a whole matrix full of crap and an input vector full of crap. I'm gonna say like N1, N2, N3, N1, 1, M1, 2. So on a CPU, to do this matrix multiplication, it would sequentially take these numbers and multiply them, these numbers and multiply them. On a GPU, there are going to be actual transistor hardware that does all these multiplications in parallel in physical real-life space next to each other, and then adds them all together, again, physically, in parallel with all the other stuff that's going on. And so the reason why they were originally done, the reason why they're called GPUs is because this is what happens in computer graphics a lot. Graphics is geometry, and geometry is linear algebra. These are vectors that encode physical space, three-dimensional space, three-dimensional vectors. Turns out machine learning is the same thing. It's just instead of three-dimensional space, you have a 4 billion dimensional space. But same hardware.
So when you rent a virtual machine, you either pick a GPU or CPU, or you can't do that.
Good question. The GPU virtual machines have both a CPU and a GPU. It's just that while the CPU virtual machines might have like the CPU virtual machines might have 96 CPUs in them. So you can have 96 computer programs running in parallel. The GPU machines might have one CPU, but a really big GPU that can do a lot of matrix multiplication. So the idea is that, with the exception of GPUs, any series is going to have compute memory and all the other things a computer does. It's just that that series is what they're emphasizing in it. It's when you pay more money, you're paying more money for compute, or you're paying more money for memory. In the case of GPUs, they say, oh, you want to do a lot of matrix multiplications. Well, you're going to pay more money for that, and we're not going to we're not going to charge you for a lot of memory or compute. We're not going to give you a lot of that, because we know that really what the care is doing this. And if you're taking a picture of this slide, I urge you to wait 1 minute, because if you just want to use a virtual machine on the cloud, as of, God, I always have to like update this because they keep changing the numbers. Like 3 years ago it was N1 and now it's N2. If you just want a virtual machine to like type terminal commands in and run code, these do not have GPUs. These all cost about $2 to $3 to run for a 24-hour day. AWS go for a T3 large, on Azure go for a D2 V5, and GCP do N2 standard. And you don't have to choose these. You can choose one that's very slightly bigger or smaller. But if you don't care, start there. So now let's talk about their twin, the twin to computers, storage. We were talking about storage in these computers. You have to be able to store your code somewhere. We call that in the cloud block storage. This is the fastest, most effective storage because it's connected directly to the virtual hardware. Usually you have one block storage device per virtual machine, and it's somewhere in the range of 4 gigs to half a terabyte. You can think of that as how, like, you could buy a 64 terabyte hard drive, but it would be in an external box that you'd keep on your desk. The stuff that's actually in your laptop, it's usually the range the block storage is at too. And that costs the most money. It costs about 16 cents per gigabyte per month. Because it has to be in very close proximity to the machine that's using it. And it cannot be shared easily between machines. The same way it's not easy to take the hard drive in one laptop and plug it into another laptop. You usually use a thumb drive for that. And so that is what file storage is. File storage is generally the most flexible. It's good for storing hundreds of terabytes of data in the cloud, and it costs an order of magnitude less. Talking like 6 cents per gigabyte per month. These are some brand names for these things. On Amazon, it's called Elastic Block Storage, Elastic File Storage. These are, when you're getting started in the cloud, the things that you'll use most often. The main drawback of using file storage is really performance. If you are writing a bunch of code that needs access to a lot of data, then you'll find that code runs much slower if the data is stored on file storage, compared to if it's stored in block storage. The way that people deal with this is that usually they will keep their whole data set in file or object storage, and they will copy the parts that they need to do work on into a smaller block storage, and then delete it when they're done. And so continuing this trend to the extreme end of the spectrum is object storage, which costs about 1 cent per gigabyte per month. You can store as much data as you want. There is no upper bound. And generally, this is seen as the most cost-effective way to keep data in the cloud. On that NIMH data stuff, I am willing to say with great certainty it is stored in cloud object storage, whether or not that's how you ultimately are given access to it. If you are storing data sets, eventually you want to learn how to store them in cloud object storage. If you take nothing out of this hour and a half that you guys are generously spending with me, it's that object storage is worth learning how to use because that's where you store a lot of data. We can get into much more detail about object storage in a few minutes, but fundamentally, it is used as less as like a folder with a bunch of files in it, and more as sort of like a Dropbox type situation where you upload and you download individual files. You say, oh, I know I have, do you guys use HDF5 files? Does that show up in your research? Depends on the field. I know some scientific fields store large clumps of data in files called HDF5 files. Whatever package you guys use, .zip files, .tar files, there might be an object storage container that has individual patients' data balled up into a zip file. And so you download a set of those zip files onto block storage. You do work with them, and then you delete it when you're done. See, what do we got next? Workflows. So I already started talking about workflows, the way that you would do all this stuff. Oh dear, my computer is getting slow, which means I think it's running low on battery. You know, I'm going to unplug my screen and plug my power in. And, you know, people on Skype or people on Zoom, if you want to chat, just unmute and say hi. I will probably not be able to see the Slack screen. Shoot. Me. Forgive me. It's Friday. Okay. Wake up. Woo. Okay, meeting, hello camera. Okay, online people, Tien, can you hear me?
Yes.
Wonderful, good, okay. So, I was talking about how we might use object storage. More broadly speaking, when we're using the cloud, what we're thinking of is using our laptop as a dumb terminal, the way we saw the groovy 1970s supercomputer. Actually, that was the 1980s computer. You can tell because if you watch the movie Tron, that's how computers look in that movie. That's when they made it. The way that this looks is that in the cloud, we rent a virtual machine and we have our data set, probably in object storage. And we access that by running a Jupyter Hub server on our web virtual machine and by logging into it using Chrome. How many of you have used SSH before? Yeah, so instead of doing this, you could just log into this machine using SSH. It just looks like a Linux computer from your perspective. You do your work, you run your code, you probably get the code to this machine by uploading it to GitHub and then downloading it to here. You can also access files on these virtual machines as like remote drives on your laptop. That can be hard to set up, but if you're doing a lot of this work, it could be worth it. Then when you're done, you turn that machine off. And so this is what we were talking about in terms of object storage. The idea is that you download what you want. We might call this staging your data close to where your code runs. Then you run your code that produces outputs, and you upload those outputs to object storage as well. And you delete all the files that you staged on your local computer. You don't actually need a virtual machine to do this work. You can work with object storage on your laptops. You can just download files from object storage directly to your laptop on the desk right now, work with it on local code, and then upload your results to object storage when you're done. You can treat it like Google Drive or Dropbox. Not as user-friendly, but more or less the same thing. And if you want to do, one of you mentioned in Slack that when you're working in the cloud, you might want to figure out how to modularize your code to split it up and run a bunch of versions of it in parallel. This is a really useful thing to do in the cloud because it's easy to rent a lot of computers for a small amount of time and then get rid of them. So if you want to, say, do a machine learning thing, a matrix multiplication without a GPU, or if you want to do something that GPUs are not good at doing, like you want to compute like a large sum over huge amounts of data, and so you can compute that in batches and do fancy, clever things to speed up the work you're doing. You can rent a whole cluster of computers. Cheap computers, expensive computers, doesn't matter. You might rent a cluster of 100 computers for 1 hour so that you can take your code and run it on different parts of the data, but all at once, all next to each other in a little neighborhood. Maybe you actually rent a GPU cluster, some computers that have GPUs on them, and you rent that for 1 hour, and you rent the CPU cluster for 30 hours. You can see how you can really avoid paying for things that you don't need, because you can rent all these things for small amounts of time. And Dask is a really nice Python package that lets you distribute computation from one machine to a cluster of many machines. That's something that's interesting to you. Check it out. It's called DASK, D-A-S-K. And so this is a common way that people will use the cloud. They will have data in object storage. They will create a single virtual machine that they will do their work from. And then from that virtual machine where they're doing work, they will create a CPU cluster or a GPU cluster to farm out their computations to 100 tiny computers working in parallel. This is one of the most exciting things that the cloud can do. People who do work in protein folding have been using the cloud to do their work for a long time. This is one of the early things that the cloud was a real success for in biology and chemistry research. Was that they could try a bunch of different configurations of protein folding to see which one bore fruit and do them all at once next to each other so that they didn't have to wait and do them sequentially. If you got the money, you can do it. Or if you have credits, which stand in for money and can be gotten very often from these cloud platforms because it looks good for them that researchers are doing things on their platforms. They like being able to say, so-and-so discovered a brand new molecule using our computer power. All right. That's all I got on workflows. Next is like probably the most dry part of this workshop. So before we go into that detail, what questions do you guys have about workflows or other? I want to take a break and talk less. You guys talk more. Say something. Please. Yeah.
Question, but it's not, I mean, I guess it's related to this, but I don't even know how related to this it is, but sometimes I'm in charge of moving data from like XNAT to our like HPC.
Mhm.
And I'm wondering, well, I don't know the best way to do it, because nobody's ever told me the best way to do it. But I'm wondering if you have any opinions on a way that is efficient, like to move like lots of data onto like a remote server with HPC.
Yeah. How do you move lots of data onto a remote server? I guess I have two questions. Where does the data start and how much of it is there?
Well,
Roughly.
for example, the last like MRI data is there's a lot of gigabytes involved with that.
Mhm.
So I moved to like 10 subjects and each had like 200 gigabytes that I was moving
Okay.
of like or DICOM files.
Yeah. It's from like a lab machine that's near the MRI.
Yeah, kind of. It's like they put it onto like this like it's called XNAT. I guess it's like attached to the MRI. I don't know exactly how they do it on the other end. All I know is I log in and I hit download and then it takes forever.
Mm-hmm.
And then I have to upload it and that takes forever.
Yeah. So that's a great question. How do you move data effectively from lots of data from one place to another? And so there are a few different ways to do it, and it depends on your organization and what they have access to. But the most fundamental principle that I would put forward when you're thinking about this question, and it's a spectacular question that every person in this room is going to think about at one point or another in your careers, unless you go into something completely different, like, you know, confectionery baking, which is a very nice thing. And I've had points in my life where I wanted to stop doing everything and go work at a science base in Antarctica baking bread. What you want to do is reduce the number of computers that the data has to hit between source and destination. Which is to say, you want to find a way to avoid having to download it to your laptop before you then upload it to the HPC cluster. And the other thing is, if you can at all manage it, try to get as close to the backbone of the internet as you can. Which is to say, when you do things on your laptop, it's going over a Wi-Fi to that thing up there, a wireless antenna, and it goes from there through a corded line to the wiring closet, which goes to the arterial networking connection for this building, which goes to the university point of presence internet hub, which is in the tower that has the big UW logo over there. And then from there, it goes into the internet. And the idea is each of those links has less and less bandwidth, is slower, and has more to do before the data gets where it's going. Things like HPC clusters are usually connected directly to the backbone of the internet, or if not, they're connected directly to the point of presence for the university that then goes to the backbone of the internet. The idea here is that if you have to download something to a machine in a building, that's probably going to be slower than downloading something to a machine in your HPC's data center. So what I would really want to do is figure out how to log into XNAT from an interactive Slurm job or from the gateway box.
Try to do them.
Yeah. No, that,
No, it like doesn't even show the like X not will not like load in there. or
yeah,
show up.
so,
Yeah, so I've tried a multitude of different ways.
yeah,
I've tried, we had a pipeline for a while, but then our HPC, like they changed things. It broke the pipeline,
yeah,
so now I'm just suffering through it.
I'm
But
sorry.
yeah, and I don't really understand it. I guess like there's like a specific XNAT server that they use like for our university, so it's not even like this XNAT, it's like a different.
Yeah,
XNAT.
yeah. Yeah, I mean, this looks, I think this is just the generic website for
Yeah,
the software,
yeah,
but
yeah.
yeah, so here's what I would do in your situation is if I have to do it once a week and it's annoying, but it's like not that big of a deal, just deal with it.
Yeah.
If it's a problem, or if like it seems really stupid that I have to like do it this way, then I begin working with IT to figure out how we can get a direct networking link between wherever our XNAT server is and wherever the file servers for the HPC cluster are in. Because the thing about HPC clusters is, you know, we're asking good questions like, what's the difference between HPC and cloud? And there aren't that many differences. HPC clusters are built basically like this. There are file servers, machines that store data. And then there are gateway machines that you log into and submit jobs from. And then there are machines that run the jobs. And so what you want to do is talk to IT and say like, look, guys, I know that this is a pain in the butt for you, but this is actually kind of your job. And we have an MRI machine with data on it. And that goes to an XNAT server. How do we connect the XNAT server to the file servers? How do we get data directly from the XNAT server to the file servers? Because when we're talking about data transfer, we want to reduce the number of hops. We don't want to have to hop onto our laptop, onto the gateway box, onto the file servers. We want to just go straight there. At the University of Washington, the way that we do that is with a thing called Globus, Globus. How many of you have interacted with Globus before? Yeah, I've seen the name float around. Globus is one of the many ways that people try to have really wide fat channel connections between different machines so that you can get large data sets into an HPC cluster or into the cloud. And it's all fundamentally trying to do exactly what we're talking about here. Reduce the number of computers data has to move through and reduce the number of times it has to go over really narrow links like the wireless.
Do you think IT, is that a question I would ask IT about Globus?
Yeah, is it possible for us to connect the HPC cluster to make it available as a Globus endpoint? They'll probably say no, if they haven't done it already, because it costs money, and it's the thing that like, the way that my boss and I do this at the University of Washington is we find enough people with the same problem, and then we go to IT bearing metaphorical pitchforks and fire and say like, just give us a dang way to connect the file servers on this thing effectively to the sources of our data. Maybe what IT will say is, oh, I mean, you don't need Globus, use this thing and that thing. That's great.
Sell a solution.
Yeah. The fundamental thing and the tricky part here is, and I apologize in advance because I presently half of my funding comes from UW IT. Thank you, UW IT. Is that you need to convince IT people to help you, because technically what they should be, their job is to help you do exactly the kind of problem you're describing there. But they need to be reminded of that sometimes. And it can really help to do a little bit of ground research about exactly what you're doing by being in this workshop right now, and by trying to get XNAP open directly on the node in the thing. Like, that was great ground research to when you're talking to them, say like, look, I've tried doing this. What I want to do is not have to download the files to my laptop and then upload them there. And by the way, if you do end up having to do it on your laptop, just make sure you connect it to a wire in the wall.
Yeah. I do on my PC, that's the wired way, a
Yeah,
lot faster.
yeah,
But it's super inconvenient, because then I have to like,
leave it there.
yeah.
Well, something else you could try doing is getting a Raspberry Pi. So the thing about those like super cheap computers, it's Raspberry Pi, like PI. This little buddy is
Is physical?
yeah, it's physical. This is not the cloud. This little buddy is like the size of a deck of cards. It usually costs like about $30-ish. It's super underpowered. It's not good at doing a lot, but it does have Wi-Fi. It has almost no storage on it, so you would need to like get a external hard drive and connect it over USB. But hey, you can leave that under your desk and run it. You log into this thing over SSH like it's a Linux machine. It is a Linux machine. It has Linux on it. So this kind of thing is great for like download some stuff over the weekend, upload it to the thing, whatever.
Do you have to connect it to a monitor?
You can, depending on the Raspberry Pi that you buy, some of them have monitor connections. So the like default one has no monitor connection, and it has no. They might have a network connection these days.
That's what I'm wondering, is then how do you know, like, because if I'm downloading and then uploading it.
Yeah.
I guess my question is, then how would you know what you're doing on
You-
that thing without like seeing it?
It's a great question. You log into it remotely from your laptop.
What?
Yeah, so I'm on my laptop right now. If I wanted to log onto a remote machine on, so this is my laptop. Well, you guys can see all my stuff. My department has it's not a HPC, it's just it's an LPC, a low performance cluster. Just has a C, it has a cluster. My department has a bunch of machines. It's an instructional cluster, an IC. It's for letting our students get good at running Linux commands. I work in the CS department. It's called at2. SSH at2. SSH is a command that connects my terminal remotely to this machine that's sitting somewhere in the Gates building. So that's how you would connect to your Raspberry Pi. You'd be on Wi-Fi that's connected to the same thing as the Raspberry Pi is. And then you SSH into Raspberry Pi. And now you can run commands on it. You can download things, remove things. One of the reasons why I want to emphasize this is that this is how you connect to virtual machines in the cloud too. It's just that for those virtual machines, you pay by the hour. And for the Raspberry Pi, you pay $30 once. There are a lot of things you can do with the Raspberry Pi. They're useful. You can run an ad blocker on them. It's fun. There are other alternatives to Raspberry Pis too. This is just the biggest brand name. But yeah, this can be good. IT generally doesn't like it when we do things like this, because technically, you run one of these things 24/7 and it's accessible from the outside internet. If you set it up to be able to log into this from home and it's sitting in your room in the university, that's a security threat, because if someone on the wide internet is able to hack into and take control of this, then that person is now able to appear as if they are sitting on campus when they are not.
So I shouldn't say to IT, please help me get XNAP or else I'm gonna buy a Raspberry Pi.
I mean, no, that's a great threat. The thing is, once they say, well, we can't help you, just don't admit that you're actually buying a Raspberry Pi. You know. There will be people who would help you with that too. The idea is that there are a lot of reasons to not do things like this, one of which being hypothetically, if you're away for a program like this, if you have something running in the cloud, you can manage it from your laptop. You can turn it off and on again, delete it, create a new one. With the Raspberry Pi, if for whatever reason you can't log into it anymore, you have to physically find where it is and like fix whatever is going wrong. So it's about adopting, it's a trade-off between adopting responsibility for managing the hardware yourself versus it being really cheap and having to pay someone to manage things for you. Well, we have 5 minutes left. Part of the reason why I was like priming you guys for questions is that there's a lot of stuff in this slide deck, partially because different years that we do this workshop, different groups of people have different interests, and so we can talk about all sorts of different things. I encourage you guys to look at the rest of this as you're interested. I'll give you a brief tour of the other slides that are here, and this will be up indefinitely. We talk about organizational structures. So if you were to log into a cloud, these are the terms that would show up that they would expect you to know. On Azure, you're going to be thinking about subscriptions and resource groups and Active Directory. Actually, I should change that. It's not called Active Directory anymore. It's Entra ID. Microsoft always changes their brand names. On Amazon, there will be root accounts and organizations. I hope these charts are useful to you if you ever need to actually start doing things on a cloud platform. There are a lot of ways to do things on a cloud platform. The most obvious immediate ways, you go to azure.microsoft.com and you start getting things set up. That's a web console. There are a lot of other ways to do things, like from a terminal. You can use commands to purchase a virtual machine or delete a virtual machine. We've got meta discussions about learning to cloud. I think that these are useful tips about how to go about trying to use these things when you are researchers who don't necessarily care about information technology. And then I have a bunch of really nitty-gritty details, such as figuring out whether you need a compute-heavy or a memory-heavy virtual machine. What does your research need a lot of? These are commands that you can use to figure out how many CPUs you can actually take advantage of or how many gigabytes of RAM you need. We talk about ways to save money for virtual machines, ways that you can get compute for cheaper by making some trade-offs, by making some sacrifices. And then how to put together budgets for these things. So with that, I think we are at 5 p.m. It is on Friday, and so I'm assuming that what you guys want to do on 5 p.m. on Friday after this is to log into AWS and start figuring out how to set up your own Jupyter Hub so that you can imagine you're an IT person who can tell researchers that it's not your problem to fix their problems. Or you can go and enjoy spectacular Seattle weather on Friday in the middle of summer and have fun hacking on things next week, because I think this is a really cool program. I'm really glad you guys are all here doing this stuff. Cool. And I'm also around for a few minutes if you guys have any questions. Yeah. All right. Thank you, everybody. Oh, and stay in touch. Send me emails if you want to. That's my email address.